In this video, we will talk about the independent samples t-test. This is a very useful test that is often seen in research. It is a statistical test for two sample means. The two samples must be independent for this test to be applicable. This means that they have to concern different entities that are not affected by one another. This test concerns the hypothesis that the means of the two independent samples are not the same. That is, that they are different. Their difference is not zero. In other words, this tests the hypothesis that the two samples are not sampled from the same population, but from two different populations with different means. Correspondingly, the null hypothesis is that there is no difference between the two means, that the two means are equal, or that their difference is equal to zero. Let's work through this with an example. In this example, we will consider two variables because the t-test is only possible with two variables, one quantitative and one qualitative with two levels only. That's how the two groups are formed. So the quantitative variable here is vocabulary, raw score on a test of receptive vocabulary, and the qualitative variable is sex. And for the t-test to work, the qualitative variable must be the independent variable, and the quantitative variable must be the dependent variable. The question that we will ask is whether girls and boys in kindergarten differ in receptive vocabulary. So if we have a group of girls and a group of boys, are they going to have different mean vocabulary? In cases like this, a difference between two groups is the same as saying that there is a relationship between the two variables. If vocabulary is related to sex, then the different sexes will have different average vocabularies. If vocabulary is not related to sex, then the two sexes will have the same average vocabularies. In this example, we'll use a sample of 15 girls and 15 boys with mean raw scores on the vocabulary test equal to 60.7 for the girls and 67.9 for the boys. And the corresponding standard deviations for the two groups are 10.3 and 12. The question is, are these data consistent with sampling from a single distribution, one population? That means no difference in the population means, so one population, that is our null hypothesis. Alternatively, if the null hypothesis does not hold, must we conclude that the populations of girls and boys have different means in this vocabulary test? Let us first look at the histograms for girls and boys side by side. So girls are in purple, boys are in blue. And we can see the bars for the different ranges of raw scores. Here is from 45 to 50 points, 50 to 55 points, and so on until 90 to 95 points for these kids at this age. Each sample has a mean and standard deviation, and we can plot the normal curves with the same mu and sigma as the mean and standard deviation of the two groups. So these are the corresponding normal curves for these data. Since our analysis only requires the means and standard deviations, this is the same as throwing out the original data and only keeping the two curves. So this is what we have to deal with, and these are the two means of the two groups, the two different samples. Are these two means statistically different? One thing we could do is to plot the confidence interval, to calculate and plot the confidence intervals for the two means. And here we can see that they're overlapping. However, we should not conclude from this that the means are not statistically different, because these are not independent and fixed. The two group means are not fixed values like they were in the one sample t-test. They also depend on sampling. So if we had sampled a different group of girls or a different group of boys, we would have gotten a different mean. There is some uncertainty in each mean, which is precisely what is reflected in the two confidence intervals. But then this means that the probability of these coming from a single population with one mean must combine being higher than the true mean on this group and lower than the true mean for this group, so that the two means will actually meet somewhere here. So this is nothing like the case of the fixed value, and therefore using the two confidence intervals to make this judgment is not appropriate. We need a different way to evaluate the distance between the two means. This is what we're interested in, the difference between the mean for boys and the mean for girls. And we want to evaluate this based on some measure of standard error of means so that we can get a t-value for it. What is the relevant standard error here? It cannot be the standard error for boys, and it cannot be the standard error for girls. It has to be the standard error of their difference. This is called the pooled standard error. The pooled standard error is in fact the standard error of their difference. This is actually very simple to calculate if we assume that the standard deviations of the two groups do not differ. Then we can simply average the variances of the two groups. So if you look at this part here, this is the average of two values, and this value here, the square of the standard deviation for the boys, is the variance of the scores for the boys, and the square of the standard deviation for girls is the variance of the scores for girls. So this is the average variance of the two groups. And then we apply the square root so that it becomes like a standard deviation. That is the pooled standard deviation for the two groups. And then we divide by the square root of the total number of children to get our estimate for the standard error. So this is our pooled standard error. This formula is only valid for equal sample sizes, equal group sizes. If the two groups have different numbers of children, then we need to weigh each variance by the corresponding number of children, and the formula gets a bit uglier than this. This formula also does not apply if the standard deviations of the two groups are different. This is just the simplest possible case, so you can have an idea of what the pooled standard deviation and pooled standard error mean, and the way in which they're conceptualized and can be basically calculated in the simple case. Note that here we have the total sample size, so both groups, twice the n, but because of this 2 and this 2, then it ends up being just the square root of n, and this is the number of children in one group. There are many different variants of this formula that you may see in books or online, and they all turn out to be equivalent. This is just the simplest possible form. Now, how do we use this pooled standard error? Well, we just calculate a t-value. We subtract the two means to find their difference in units of measurement. And then we divide by the pooled standard error. So that would be the formula we just got on the previous page, and substituting the actual numbers, so means and standard deviations for the two groups, and sample size, and we get a value of 1.76. This is our t-value, and what it means is that the two means, the mean for vocabulary scores of boys and the mean of vocabulary scores for girls, are 1.76 standard errors apart. And when we say standard errors here, we refer to the pooled standard error that is calculated based on both groups. So here we have a standardized distance of the two means in terms of standard error. The p-value for this one is 0.089, which is greater than our alpha level. Therefore, we cannot reject the null hypothesis that the two means are equal. That was the null hypothesis, that their difference is equal to 0. In other words, that they are equal. Or in other words, that the t-value is 0. That null hypothesis cannot be rejected. In other words, we say that the two means are statistically indistinguishable, and that our two groups are consistent with sampling from one and the same population. These are all alternative ways of stating the same conclusion. There is one piece of information that I haven't mentioned yet, which is very important, and that has to do with the degrees of freedom. I haven't told you what value I used to look up that p-value. To find out how many degrees of freedom we have here, we need to consider how many data points are free to vary in this situation. There are 30 data points, but they are in two groups of 15, and we actually calculated the mean of each group. So we summed up the values in each group separately. Therefore, we have removed 1 degree of freedom from each group. That adds up to 2 constraints in total, not just 1. So 2 means 2 constraints. Therefore, we have to take out 2 from 30, and there are 28 degrees of freedom for this test. So 30 data points, 2 means calculated. That means we have 28 degrees of freedom. And in general, for the independent samples t-test, which always concerns a comparison between two means, the degrees of freedom are equal to the total of the two sample sizes minus 2. So n1 plus n2 minus 2. And this holds even if the two sample sizes are not equal. This number is, of course, very important because we need it to look up the p-value on the appropriate t-distribution. One issue that you'll see mentioned in all statistics books is whether we should be running a one-tailed versus a two-tailed test. Let's see what that means. In our case, as we've stated it so far, the null hypothesis is that the two means are equal. In other words, that t is equal to 0. Because if x1 equals x2, then their difference will be 0, and the difference is on the numerator for calculating the t. So that's all saying the same thing. And the alternative hypothesis that we're examining is the opposite of that. So the alternative hypothesis, what we are left with if we reject the null hypothesis, is that the two means are not equal. In other words, that t is not 0. The difference of the means is not 0. That's our alternative hypothesis, and it doesn't say which of the two means has to be bigger. Either one can be greater than the other and still get a statistically significant difference. And that's just fine. We could conceivably be interested in a more restricted hypothesis. We could choose a directional hypothesis, which means that we might only be interested in the possibility that the first mean is larger than the second. Perhaps the possibility of the opposite, of the first mean being less than the second, is for some reason inconceivable or theoretically uninteresting. In that case, we would want to reject the hypothesis that x1 is less than or equal to x2 because this is what we're interested in testing. Stating the problem in this way is the same as considering only one of the two tails of the t-distribution, because the t-value includes in its sign which of the two means is greater. So if the one mean that we put in first is greater, the t-value will be positive. If the one we put in first is less than the second one, then the t-value will be negative. Therefore, positive and negative t-values are associated with a different group being greater than the other. And if we're only interested in one of these possibilities, then we're not interested in both of these tails. This is the left tail that concerns negative t-values, and this is the right tail that concerns positive t-values. We normally run two-tailed tests by setting this one here, and then we consider both of these areas together. And this is the probability for both of these together. If we were interested only in the possibility that the first mean is greater than the second, then we could choose to only consider this tail for positive values of t exceeding our observed value, and choosing tail here to be able to do that. Alternatively, we might be interested only in the possibility that the first mean is less than the second, so only consider extreme negative t-values, in which case we can set up our probability calculator to look to up to, so that we only get the left tail, and this would only make sense with a negative t-value. So the probability here is exactly half of the probability with both tails, because this distribution is symmetric. So this is fine from a statistical point of view. However, in practice, we don't do that anymore. Although there's nothing wrong with it statistically, this possibility has been abused because it results in a lower p-value. In conjunction with the fact that the conventional alpha level of 0.05 is seen as too relaxed by many researchers today, it has become a sort of an unspoken standard that we always run two-tailed tests and never consider one-tailed tests or directional hypotheses, no matter how reasonable they might be from a statistical or theoretical point of view. So always run two-tailed tests, in other words. Another important thing we need to have in mind concerns the assumptions. What must be true for the results of this test to be interpretable? The calculation of the t-value and the probability obtained by looking it up on the t-distribution depends on certain assumptions that were made when the procedure was devised. So these are mathematical prerequisites. The first thing that must hold is that the data must be normally distributed, because the derivation depends on the normal distribution of the data. If the normality is violated, does not hold in our sample, then we cannot use the t-test, and we have to use a non-parametric test instead. The second assumption is independence. That means that each data point is totally independent from every other data point. It's not affected by it and does not concern the same entity. For example, no two measurements from the same child. Independence is sometimes violated in a systematic way when, for example, we have more measures from the same child, as in a longitudinal design, or when we want to compare different tests. In that case, the data are dependent by design, and we must use a different type of t-test. We cannot use the independent samples t-test that we just discussed here. The third assumption is that the two samples must have equal variance. The good news about this assumption is that there is a fine workaround when it is violated, because you can just use a different version of the t-test with a bit more complicated formulas, but we don't have to calculate them manually anyway. We just have to check a different box on the computer. And instead of running student's t-test, which is what I just showed you because it's the simplest possible, we can run a Welch's t-test, which takes into account that the two variances may be unequal. And then the results of the test are valid and interpretable. What about the size of the effect? As we've said many times before, an effect refers to a relationship between the variables. So if two variables are associated, that means one affects the other, statistically speaking, or that one is predictable from the other. So how strong is this effect? How large is this effect is a valid question. In the specific context of the t-test, the question is, how big is the difference between the means? And when we ask a question of this sort, we aren't referring to the unit of measurement. Of course, we could just report how many points or centimeters or whatever we're measuring, the two means differ. But when we talk about effect size, we're interested in a standardized measure of the effect. For the t-test, the relevant statistic for effect size is Cohen's d. D is equal to the difference between the two means divided by the pooled standard deviation. This is not the standard error of the mean. This is the standard deviation that can be calculated from the two samples. This is very important to remember because it expresses the difference between the D and the T. When we use the standard deviation here, this is dividing the difference between the means by the standard deviation. So this answers the question, how many standard deviations apart are the two means? That's how we measure the size of the difference. That's the effect size. If we divide by the pooled standard error instead, then we're answering a different question, namely, how many standard errors are the two means apart? That would be the t-value, and that value is affected by sample size. So as sample size grows, t grows with it. But as sample size grows, d doesn't grow, it just converges to a stable value because we increasingly obtain a more accurate estimate of the standard deviation. So d tells us how many standard deviations apart the two means are, which has a stable answer, and t tells us whether we can detect that difference with our sample size. So the two values are to some extent related because you can detect smaller differences with larger sample sizes, but they're very definitely not the same thing. They answer completely different questions. The way to calculate the pooled standard deviation, we have in fact already seen when we talked about the pooled standard error. You will recall this formula. We're not going to divide by the square root of the sample size here. And of course, this is the simplest possible version of the formula where we are assuming that the two groups have equal sample size. This formula only works for equal n. There are more complicated formulas for unequal n, where each standard deviation is weighed accordingly. And finally, to report our result, we use the same format we introduced with the one sample t-test. Note the different degrees of freedom. It's n-2 here, the t-value with 2 decimal digits, the p-value with 3 decimal digits, no leading zero, spaces around the equal sign, and italics for T and P. And it is becoming increasingly common to report and occasionally to require reporting of this effect size. So Cohen's D is reported, it requires a leading zero because it could be more than one standard deviation difference. So this zero is required. And people are also increasingly reporting a confidence interval for the effect size. So this is the 95% confidence interval for D, which in this particular case runs from minus 0.12 to plus 141. The effect size has a confidence interval that includes zero because it runs from a negative to a positive number. So zero is within this range. And that's why our test is not statistically significant. The difference between these two means is not statistically significant because the confidence interval for the effect size includes zero. So it's compatible with zero effect.